Hello everyone, I'm Sijie, Shen, and it's my pleasure to introduce our work about bridging the gap between relational OLTP and the graph-based OLAP. It is a collaborative work of Shanghai Jiao University, Alibaba Group, and the Shanghai AI Laboratory. JP, short for graph analytical processing, is widely used in many different scenarios. For instance, social media networks use JP algorithm like PageRank to better understand the relationships between users. And on the other hand, business tends to use graph traversal or graph neural networks to provide valuable recommendations. Most of the data is stored and updated in relational OLTP systems. And we were faced to perform dynamic JP while updating data. However, performing dynamic graph processing on relational data sets can be quite inefficient. Typically, users have to rewrite their graph operations by the relational operations. Moreover, using join operations to express graph traversal can be very costly and produce large intermediate results. Let's talk about some requirements of dynamic JP. The first requirement is performance. This means the performance of OLTP and JP under the dynamic JP workloads should be comparable to that done on the specific systems. In addition, the analysis results should be fresh, which means that the time gap between when data is updated and when data can be read should be minimal. Now we introduce two existing solutions for dynamic graph analytical processing on relational data sets. The first solution is to process the data offline. This approach requires combining OLTP systems with graph-specific systems. To explain how this process works, the first step is to commit the data in the OLTP system by transactions. Next, you need to conduct an ETL process to traverse the relational data into graph data and store it in a graph system. Once the ETL is done, you can submit the JP queries to the graph systems. This approach can provide good OLTP and JP performance, while the main drawback is that it can result in poor data freshness due to the costly and the lengthy data transformation process in ETL. To invariance the graph model and shorten the freshness, some systems are designed to process the JP online. It means that the OLTP systems also support graph processing. Some OLTP systems support graph processing by a graph extension, such as a language extension or a storage extension. However, the execution is still inefficient due to the relational operations. A new trend is called graph database systems that store the data as a native graph model, such as Neo4j or Tiger Graph system. This solution can achieve good freshness. However, due to more complex data management, the performance of transactions in graph database is significantly slow. A new computing model called hybrid transactional and analytical processing, shorted for HTAP, provides an opportunity for the dynamic JP. In HTAP systems, users perform real-time queries on data generated by transactions. To achieve high performance and data freshness, state-of-the-art HTAP systems often use a loose-coupled architecture based on the transactional logs. This architecture supports two isolated and dedicated execution engines for high performance. Additionally, analytical processing can be performed on the data replayed from synchronized logs, which provides the good data freshness. Based on the advantages of HTAP, we extend it for HTGAP, which means hybrid transactional and graph analytical processing. It provides the capability of GAP on the analysis component. So we present GAT, an in-memory HTGAP system for dynamic GAP. GAT is based on the HTAP architecture and includes at least 2 key components. The first component is the relational graph mapping. Due to the different data semantics of relational and graph models, we need to maintain a schema mapping to convert data automatically. The third component is a dynamic graph storage. It can handle concurrent reading and writing operations. For high performance and data freshness, it uses log replayers to update graph data, which can be read by graph analysis. To support HTGAP workloads, GAT should address at least 2 unique design goals that have not been addressed in previous HTAP systems. First is the transparent data model convention. Instead of interface convention, GAT does not require users to rewrite their queries or requests. Users of GAT also do not need to care about how the data is converted. Second, we need an efficient dynamic graph storage because both read and write performance are important. In particular, GAT should guarantee read locality when supporting graph updates. Now we talk about some designs that address the first design goal. To prevent users from rewriting TP and JP requests, GAT decouples the interface for data manipulation and the model convention, like the DML and the DDL in the relational databases. GAT provides 2 types of interfaces. The first one is called data manipulation interfaces, like the DML languages in the SQL databases. It is provided by the original execution engines. Users can write the requests as if they were on the specific engines without any modifications. And the graph extraction interfaces are more like the DDL languages in the SQL systems. It is provided a newly designed model called RG mapping. This type of interfaces is used by system administrators that allow them to define the mapping only once, instead of for each request. RG mapping, this model provides expressive interfaces for extracting graph from relational models. GAT defines the graph use dedicated table names and column names. Each vertex type corresponds to one relational table by its relational table name. And the edge types should specify the table name and the primary key to use to specify how the vertices are connected by this type of edge. And the property storage corresponds to a column in the table. Overall, this approach allows for transparent conversion between relational and graph models. Users do not need to rewrite their queries and can reuse their existing requests. Next, we talk about the dynamic graph storage and some design on it. There are 3 problems with existing general-purpose dynamic graph storage. First is about the topology storage. CSR is a typical and immutable graph storage with good edge scan locality. Well, when a new edge is added, it should be costly to move the edges for a free slot for this new added edge. And the adjacency list-based structure supports updates efficiently, while the edge locality from adjacent vertices is poor. Second is about the fine-grained MVCC, which means records timestamps for each edge and each vertex. Besides the overhead of updates and checking, it also breaks spatial and temporal locality for edge scanning operations. Third is about the property. There is no efficient property storage model for all JP workloads. Fortunately, we find some key insights about the HTJP workloads. We can further optimize our graph storage by these key insights in GAT. The first one is that the required freshness of HTJP workloads, or we can measure it by the time gap between updates from OLTP and reads from JP is sufficient for the system to update a compact structure. Typically, at about tens of millisecond freshness. And the JP latency is much longer than the time gap, so the fine-grained MVCC is not necessary for the JP under the dynamic JP workloads. In addition, for the property, the access pattern is almost fixed under a single workload, so the user can decide how to store different properties by the workload and the access patterns. Based on the three key insights about HTJP, we have redesigned the dynamic graph storage in GAT and among three key aspects: the topology storage, MVCC, and the property storage. For the topology, we maintain an efficient and mutable CSR structure that divides edges into several edge segments to support efficient new edge insertion. For MVCC, we use a coarse-grained approach that batches a group of edges and uses epochs to record the time information or the version information. This allows for efficient management of the data versioning while ensuring high data freshness. Finally, we also offer a flexible property storage model that allows users to define the property storage based on their specific access patterns. Overall, these storage optimizations have been instrumental in boosting the performance of GAT under the HTJP scenarios. To preserve the locality of the edge scan, we designed an efficient and mutable CSR structure. This structure divides the edge arrays into several edge segments. Each edge segment stores edges for a group of vertices. It provides a trade-off between read and write performance. And each edge segment has a fixed initial size, and it keeps free slots reserved for new edge inserted. When a segment is full, it will be relocated with double size by the combine or write mechanism. So you can find when the edge segment is large, it is more like the original immutable CSR structure, which is good for edge scan locality, but as a pool for the edge insertion operations. When the edge segment, the size is smaller, and it is more like the adjacency list, so it will achieve the good edge insert performance while the pool edge scan in performance. So the size of edge segment provides a trade-off between read and write performance. To prevent from metadata updating when segment relocation, each vertex stores the edges is a series of edge blocks stored in the same edge segment and indexed by using logical offset. So when the edge segment is relocation, the logical offset will be not unchanged to prevent the data rewriting. Please refer to the paper for the storage details and other two storage designs. Next, let's talk about the evaluation of our system. We conduct our experiments on two machines. One served as the OLTP server, while the other served as a GAP server. We extended the standard benchmarks LDBC and TPCC to accommodate HTGAP workloads, since there is no standard HTGAP benchmarks now. So we have to extend the original OLTP and the JP benchmarks and mix them as the HTGAP benchmarks. To examine how GAT performs under various HTGAP workloads, we selected a range of GAP-specific works focusing on analytical traversal and Jingren. We compared GAT with the offline solution combined with the state-of-the-art OLTP system, the RTMH, and the graph system, graph scope. And they are the same OLTP and GAP extraction engines with GAT. For the online solution, we choose the graph database called Neo4j. Neo4j use adjacency list-based storage. To further investigate the impact of storage optimizations on GAT, we replace the GAT storage with the state-of-the-art dynamic graph storage called LiveGraph. It is for OLTP and JP performance. GAT achieves comparable performance and outperforms the online solution by orders of magnitude due to the more efficient graph storage. For freshness, GAT is comparable to the online solution and outperforms the offline solution, which avoids the whole graph loading when between the original OLTP system and the JP system. We further break down the execution of JP for detailed performance analysis and compared it with GAT using LiveGraph. We compose an extraction path into three parts: access topology, access property, and the time of computation. The performance gains from topology and property are due to our designs on the graph storage. Using the PageRank algorithm as an example, nearly about 80% of the performance improvement comes from our topology designs. We also evaluate the performance isolation by increasing the number of JP and OLTP clients. It shows that the performance degradation on OLTP is trivial, and it is about 12% on JP due to the version checking overhead. Like this. In conclusion, we present GAT, an in-memory HTGAP system extended from the HTAP system for dynamic JP workloads, which supports transparent data model conversion by graph extraction interfaces, and provided by the newly designed component called RG mapping. And it also provides an efficient dynamic graph storage with good locality. Our production code and experiment code are also open source. Thank you for listening.